In terms of the PMLs, I'm not going to delve huge amounts of the formulation, the mathematical details. All the papers of the formulations that we use are available through our publications page in the website. You will probably find them there. And it will take a day's work of workshop in a way to explain from various principles how the formulations have been developed. And that's not the point of them. So the reason for requiring PMLs, or what you call ABC, absorptive boundary conditions, is because obviously our problem, theoretically, is what you call an open boundary problem. That means that the boundary condition for that is the radiation conditions, which states that the fields decay to zero at infinity. Now, the problem is not that the fields decay to zero, is the problem that we cannot reach infinity in a computer, because obviously we don't have infinite resources, and therefore we have to at some point stop and truncate our model, and at that time, at that space position, then the fields cannot just stop, but they have to, from the field perspective, the field should appear that there is no boundary, and this artificial boundary has to pretend and mimic in a way the continuum space beyond that boundary. So that's why we'll create absorptive boundary conditions. This is a topic which is not only for electromagnetics, but for dynamics, for a lot of open boundary problems. It goes on for many, many years. And the absorptive boundary conditions is basically, as a slide in another slide on Wednesday, is predicting or dealing in a way with the fields at the boundary that you don't know what to do with them. You don't have the information to update them, and either you have to predict a value in the given the information that you have inside, or do something to minimize any reflections from that boundary. In the early days, we were trying to actually predict these values with one-way boundary conditions, as we call them, which trying to find what the value would have been given the information from the inside of the model. But that is of historical interest now, because the performance of these conditions were never really very good. They did okay at first order in a way. The more we try to improve them, the more unstable they become, more difficult to perform, and eventually we had a bottleneck in terms of performance. One of the reasons is that because the theoretical framework behind them, depending on very simple plane wave propagation in a way, which couldn't take into account all the various homogeneous waves that we might have, when scatterers are close to the boundaries. We have evanescent waves and all sorts of different waveforms than the simplistic assumptions that were based in developing these local absorptive boundary conditions. And obviously they exhibit a lot of instabilities when the order of approximation was increasing in order to make them any better. So we wouldn't really be able to use them a lot. The best performance was something around -30 or -40 dB in terms of reduction of reflections. Then Berenger came in 1994, and other scientists like Chu and Wheaton around that time, and created the concept of perfectly matched layers. The perfectly matched layers are basically layers that introduce into the model and have the ability to reduce the energy of the wave, reduce the amplitude, suck them out or diminish them without actually creating reflectors. Which is really a trick thing to do. And the way you see a PML is basically either as a non-Maxwellian anisotropic material, and material that actually doesn't exist, but it has some funny properties in a way, or in a better way, in my view, as a complex stretching of space. And I explain what that means in a minute. So they offer very good performance, a lot better performance than the previous absorptive boundary conditions, and often for the simple case, which is so independent of frequency as well, and the surrounding medium properties, which is really a very good thing to have. Now, here is what you see for the local ABCs, you know, the prediction of the boundary values when the models was finishing. And here is what will happen when you have the perfectly matched layers. Now, here we see 3 layers PML. In gprMax, the default number of rails is 10. You can customize that if you need to. The thicker the PML is the best method of increasing performance, but obviously that means that you're reducing your space where you can do work, and therefore your model gets bigger. The idea of using a a layer to absorb waves is not new. In seismics, for example, it's been used for many years in what you call a sponge boundary condition. The idea there is that when you increase slowly and steadily your attenuation in a layer, then you obviously attenuates the wave, and eventually the wave might reduce to very small amplitude, which when gets reflected from the boundary at the end of your problem, it comes back, but it then attenuates again as it goes from the same boundary layer, and eventually you get very small reflection. In essence, you can do that with physical media if you turn on your attenuation extremely slowly and steadily. But anytime you introduce some physical material variability in your model, you're bound to get a deflection. This is how electromagnetics work. If you have a variation of the electrical properties of the medium, of the physical electrical properties of the medium, this will create reflections. You can try and do them very gradually, very slowly, and it happens in what we call, for example, anechoic chambers, when we can test antennas and we're supposed not to have reflections from the walls of the lab, but we minimize them. So there are tricks that you can do, but this wastes a lot of space and a lot of effort to do that. So the PML is in the similar way developed, but the mechanics of them, it doesn't relate to real materials to create reflections. So the name means perfectly matched layer because it's a layer that is matched perfectly, at least in theory, maybe not in the digital work, that is matched perfectly to the surrounding medium. So there is no impedance contrast for the wave. So the wave doesn't really see anything different, but it gets attenuated. So, which is probably a strange thing if you're a wave to experience this. Now, here is a very simple performance characteristic on a 2D simple pulse. You see, he emptied it, it went away from the domain, and you almost see nothing coming back. If you are really very careful, you're probably going to observe that there is some smaller reflections. Reflections are always there. The thing is how to minimize them and make them a lot smaller than the actual main amount of radiation that you want to simulate and you're going to get. It's almost practically impossible to completely kill them 100%. Now, how the PML works, the best way to work with the PML or to see it is basically as what we call a complex stretching of space. That's a tricky concept, but for example, we can start with a simple description of any field, which depends on some position and time, and that real field in space and time can be seen that it's a summation of a number of plane wave modes that have a wave number k, which is a vector because it defines the position of radiation, and a frequency mode of propagation, an angular frequency. So you can get this classic A, J, omega t minus kx, where a range of these modes might exist to describe a real field. Now, in here, what we see, the solution practically is an oscillating wave. If you plot the real part of that is actually represents pretty much what is happening, you will see an oscillating wave, like a sinusoid that goes around. It's not just a sinusoid in time, it's a sinusoid in space as well. So it's probably a wave number mode with a specific frequency. Now, one of the ideas for the PML is to take the spatial variable x and convert it to a complex variable. Now, if you try to imagine what that means, is actually you struggle a lot because we really live in real space. We don't really live in a complex space. But let's, in terms of mathematics, assume that we can have a complex space variable. That formally means that we can continue, if you like, analytically our solution and equations in a complex plane instead of the real axis. So in a complex contour, if you like, instead of the real axis. And there, what will happen if we do that and properly choose our complex space variable, the oscillating waves can become exponentially decaying. But at the same time, there will be no reflections. So if we change our real space variable to a complex x tilde variable, we have a real part, which is our real space, and an imaginary part, which is a functional form of something, which we have to define what that would be. Now, if I replace space x in that equation with a complex space variable now, and I do the simple mathematical manipulations of that, you'll see that obviously when I replace the complex space variable with what is made of, the real part and an imaginary part, multiply the things out, I will end up with something which represents what I had, the first part of it, which is the oscillating solution, so the wave here hasn't really changed, but I've bolted on an exponential decaying function, which actually reduces its amplitude. So as you see, the last term of the exponential minus k of fx is actually is a real decay that I can introduce into the wave, while the form of the wave hasn't really changed. So the wave doesn't really sense a difference in the material or difference at all, apart from the fact that its amplitude start to decay. And obviously, if I do that for a while, then it will reduce enough to actually stop it with a hard Dirichlet boundary conditions, like set it to 0 or reflect it completely towards back to the domain, which is going to be more attenuated as it comes back to the main, back to the way of the main grid. If I just take a single component now and see how that will work, then again, I have this wave number kappa and the attenuation formula. I can define that this function has this specific form, a sigma, which is not a real conductivity. It would use conductivity because it's lost, so it depends on space, divided by omega epsilon naught. Now, someone will say, why you pick that and you don't pick something else? And that makes a lot of sense, and it will show in a minute why that's the case. So I assume at the moment that the derivative over space of this f function is sigma over omega epsilon naught. If I replace that into this equation, what do I get is basically over the domain that this complex function of this sigma exists, I have a real attenuation, which is given with kappa, which is the wave number, divided by omega epsilon naught, and the integral of my sigma, which is a real number, will be an attenuation. Now, the reason that df over dx was set initially to this ratio is that if I know that kappa is omega over c, which is basically the angular frequency over c is the velocity, here's the velocity of light because I assume I'm in free space, it doesn't have to be, is the phase velocity of the material, and the wave number will be defined by that. Then if I replace kappa in that equation, I can see that I kill the dependence on the frequency, and I create an attenuation factor that is actually independent of frequency. That's a quite significant result for the early PMLs, that it will work equally well for any frequency inside my model. It's still dependent on the angle of incidence, that hasn't gone, but the dependence on frequency is completely eliminated by that choice. So that's why it explains the choice of sigma over omega epsilon naught in the beginning. So if I see a Maxwell's equation, a component of a Maxwell's equation to discretize in finite difference time domain, say, for example, the y component, you see that it's obviously depending on the y-directed curl of the magnetic field. We'll see the derivatives there. What you note is that we have complex spatial derivatives. Now, we don't really like to have complex spatial derivatives in a time domain algorithm and a real algorithm. So what we do is a change of variables to go back to a real variable. And the way we do that is obviously remember that our complex space was the real part of it and an imaginary part of it. So what we see here is that the partial differential for the complex partial differential will become the 1 minus the imaginary df over dx. And then if I replace that to my equations, I ended up having real spatial derivatives scaled by a complex function. If I replace df of dx with what was defined originally and actually manipulate the j to go to the denominator, then I'll see that I have the same equations that I had, but all spatial derivatives appropriately scaled by a complex function. Now, similar to putting Debye media or frequency-dependent materials, this is a tricky situation to deal in a time domain algorithm, but I can do that. actually the PML can be seen as well as a complex medium. Another way to view the PML is a complex medium parameters, a non-Maxwellian by anisotropic medium. So once I have that, I can easily replace this fraction with 1 over S, where S is what I call the stretching function. In a PML, you call this a stretching function. So you see here the more simple stretching function, we have 1 plus sigma over j omega epsilon naught, where there is no stretching in the real coordinate. But obviously, instead of having 1 there, we can have kappa, which is k, or kappa in Greek, k for the wave number, which actually allows me to do some physical, real stretching in the same stretching function as well if I want to. Or later on, when we found out that this type of PML was not performing very well for evanescent waves and lock integration waves and grazing waves, grazing incidents, and because it has a pole at omega 0, when omega tends to 0 in this function, you see that's obviously we have a singularity there. There were an introduction of another parameter, transition frequency, as we call alpha, which that is termed the CFS, the complex frequency shifted, because of this alpha parameter is introduced in the stretching function. And obviously, researching more of that, you can combine these things together. If I say that I have more than one S functions, I can have a multiple amount of S functions multiplied together. This creates a higher order PML when I have S1 times S2 as the stretching function, actually 2Sn, or what you can recently develop, the multipole PML, when I can add them together, which is a better way of actually increasing the degrees of freedom in the stretching function to develop PMLs a lot better. Now, I develop and play a little bit with these formulations of how to do this stuff, and who have developed algorithms to do both the PML, who actually improve performance huge amounts initially. It's very relatively easy to implement because it's simple in comparison to the CFS and the higher order, but it doesn't work as well with complex models and evanescent waves, and when you put them very close to targets as much. The CFS PML has improved that. But the problem with the CFS PML is that it's difficult to optimize. There's no guidance of what your alpha should be. It's problem dependent, and there's a lot more work that is needed to make it automatic. gprMax does the simple PML automatically for you, finds an optimum sigma, and actually performs quite well. But it gives you the ability to customize all aspects of the stretching function, the kappa, the alpha, the sigmas, in any way you like. Not only that, but these formulations are more generalized to higher orders as well. So in terms of formulations, we have the split field or complex stretching of space that are theoretical equivalent. That has been shown within scaling of field components that produce the same result. But the non-split PMLs are more preferred because easier to employ into finite difference time domain algorithms. The main contenders there is what you call the convolutional or CPML by Roden and Gedney, and what we have the recursive integration PML by myself over the years that I've been developing. So I won't give you any guess what kind of PML is in gprMax. It's definitely not the CPML, which is okay, but we like a lot more the recursive integration for obvious reasons, because we like the author. So here is a paper for the unsplit implementation of higher order PMLs that allows you to do a higher order PML, which can be a multiplication of stretching functions. You can do only one if you like, or two. Doing more than two is actually not very beneficial. Any test that we've done, it doesn't really help. Or recently, the multipole perfectly matched layer PML, which will allow you to do a linear combination of stretching functions, which we'll find that it's actually easier to optimize. It's very new. This is only 2018. Actually, the paper came out 2019, I think, in print. And we'll find that this actually performs really well. But if you really want to find more information on how they work, please read the papers. There's no time to do that here. So some simple examples. 2D model, one source, this is a TE model, that's not in gprMax, that's a solver in MATLAB. And we have A and B as the output points. B is the most tricky point because it's in the corner. and we have an excitation, and we see how the error will be between a reference solution, and the reference solution is obviously the same model, but really very big, so there is no perturbation from the boundaries. So we have a reference solution that is not affected by boundaries. That's why the 2D test is easy to do. And if we see the performance, you see there are IPML at point A with the dark rectangles, and the CPML at point A with the circles, dark circles, and the open rectangles is the RIPML at B, and the open circle is the CPML at B. B is a more stringent point because it's in a corner. So you see that the RIPML performs very similar, but a little bit better than the CPML, and there is reason for that Iraklis have solved later on in another paper. But we do get a good level of performance, minus 40 dBs or 30 for this kind of problem, a very, very small 2D model. If we actually do a CFS PML and increase the alpha parameter, we see that actually the performance improves significantly. We'll go to minus 90 dB. The PML, the RIPML outperforms the CPML again. But the problem here is we find this through trial and error. Therefore, we don't have an automatic way for you to develop a PML that you can use with the alpha parameter for all problems. So it's that's why gprMax is not doing that automatically, but the code that you have is able to do that, and you can experiment and see how your PML performance improves. If we see the relative error of both CPML and RIPML in 2D test, as we're increasing the PML thickness, we see that the RIPML still performs a little better for the CPML. We know why, because the CPML in original formulation is not time-centered as it should have been. We corrected that, and it actually works really well when you do it. But you see the critical factor on a PML is the thickness. So what you need to do if you see that you have boundary problems from a PML, when you get reflections that you cannot explain and come from the edges of your model, you increase the thickness of the PML. That's the easiest way to solve the problem at the moment, or try to employ a higher order formulation that you can optimize for your own problem. But unfortunately, there is no clear guidance on that, and it's a lot of trial error. So that is basically what I wanted to talk about this, the PML. But before we go, I would like to actually address some other issues. One issue that I want to address is the use of the PML as, hold on, where is my PML? Okay, here's a simple PML demo. I have, Craig, you can see the screen, can you?
Well, we can see it. It's the text a little bit small.
So let's see if I can I improve that with a view. Why doesn't do that bigger? Okay, hold on. It's not any better, is it?
If you go to the preferences, you can change the font.
Yes. Hold on. Preferences.
There were a couple of questions that had come up on the PML, both from Pavel. The first one is the function ax of t. I think he's asking, is it a real function for the complex coordinate x also?
I mean, ax of t, it is a real function, which is it's the solution basically analytically continued in a complex plane. So the special variable is becoming a complex variable, but is applicable to theoretically, that's not applicable to all problems. If the problem can be analytically continued in terms of its solution and equations into a complex plane, then it's applicable. So the PML is not really something that's applicable to all situations. For electromagnetics and the things that we do, we can do this. And now let me find where I'm going to bid fonts. Okay, I'll go to 24. apply. Okay, all right. So that should be a bit better, is it?
Yeah, that's better. Yeah.
Okay, so basically what we have here is a frequency of 1 gigahertz, the velocity of light, a linear space of real space of 10 meters with 10,000 steps, and an imaginary variable that gives us originally zeros to half the space, and then start increasing after half the space, after 5 meters in a way. Then we create a linear time span from 0 to 10 nanoseconds with 1,000 steps. Then we define omega, we define kappa, and then we plot here the real part of the exponential, which is the j omega t minus kappa complex x. And if I plot this and run it, what you see, I think you see the plot, yeah? You see basically that you have an oscillator solution, which is right, which is what's supposed to be. And actually, when the complex spatial coordinate comes in, this solution attenuates. Now, this is perfect in theory, but obviously in practice, in discretized world, we have errors and it's not perfect. But you see that basically the type of the solution is not really affected because the wave or the mode, it doesn't really sense a change in the material. So it doesn't really change at all, apart from the fact that it's losing strength. And when it loses strength quite a lot, then actually I can truncate it at that point. I can easily go, say, for example, and increase this, and then if I run that again, you see that I can kill it a lot quicker, or I can reduce it as much as I like. So that's the concept of the PML.